Alright, continuity. Now, if f of x is continuous at x is equal to a, then the following conditions must be met. Number one, f of a must be defined. Alright. Number two, the limit of f of x as x approaches a must exist. And number three, the limit of f of x as x approaches a must be equal to f of a. So in other words, this means that for a function to be continuous at a point, the function must have a value at that point, the limit of the function must exist at that point, and that the function must have the same value as the limit at that point. Alright, let's have a look at example 22. Is the function f of x is equal to 2x plus 1 continuous at x is equal to 2? Well, the first thing we need to do is find out if the function is defined as x is equal to 2. That should be easy to find. 1. So 1, let's find f of 2. Now f of 2 would be equal to 2x plus, f of 2 would be equal to 2 times 2 plus 1. In other words, f of 2 is the value of f of x when x is 2. So wherever I see x, I just simply take out x and put 2. And this is equal to 5. So when x is equal to 2, the function is defined. The function has a value. Alright. Number 2, well, the second thing we have to do is to show that the function exists. And to show that the function exists, we have to show that the function has a that the left hand limit of the function exists, and that the right hand limit of the function exists, and that the left hand limit is equal to the right hand limit. So the limit of f of x as x approaches 2 from the left hand side would be equal to, by direct substitution, 2 times 2 plus 1, which is 5. Alright, and the limit of f of x as x approaches 2 from the right hand side is also what? 2 times 2 plus 1, which is equal to 5. Now the left hand limit of f of x is equal to the right hand limit as x approaches as x approaches 2 from the right hand side. They're both equal, and they're both equal to 5. So under this condition, we know that the limit exists, because the limit exists if the left hand limit exists, the right hand limit exists, and the left hand limit is equal to the right hand limit. Alright, and 3, so the limit of f of x as x approaches 2 is equal to f of 2, which is both equal to 5. Therefore, f of x is equal to 2x plus 1 is continuous at x is equal to 2. Alright, so three things must exist. One, the function must be defined at x is equal to 2. The limit must exist at x is equal to 2. So the left hand limit has to equal to the right hand limit. The left hand limit must exist, the right hand limit must exist, and the left hand limit must be equal to the right hand limit. And 3, the limit of f of x at x is equal to 2 must be equal to f of 2. Under those conditions, the function is continuous at x is equal to 2. Let's have a look at types of discontinuity. Alright, so the first type of discontinuity is infinite discontinuity. Now this is saying if the limit of f of x as x approaches a is equal to positive infinity or negative infinity, f of x is said to demonstrate infinite discontinuity at x is equal to a. So if the limit of a function at a particular point is positive or negative infinity, the function is demonstrating infinite discontinuity. Um, 2, you have point discontinuity. Now, if the limit of f of x exists but is not equal, if the limit of f of x at x is equal to a, as x approaches a, exists but it's not equal to f of a, f of x is said to demonstrate point discontinuity at x is equal to a. Alright, so this is like a situation where you have f of x is equal to 0 over 0. The limit of the function exists at the point, but the function itself is not defined at that point. Alright, or the function is not defined at that point. Number 3, you have jump discontinuity. This is saying if the left hand limit of f of x as x approaches a is equal to y1 and the right hand limit of f of x as x approaches a is equal to y2, where y1 is not equal to y2, then f of x is said to exhibit jump discontinuity at x is equal to a. Alright, let's have a look at example 23. Alright, in example 23 we're asked, using the graph of f of x, identify whether the function f of x is discontinuous at the given values of x. If the function is discontinuous, identify the type of discontinuity. Alright, let's just turn the page here. Alright, so what we need to look at is what is happening at x is equal to, on this graph, what is happening at x is equal to -1, x is equal to 2, x is equal to 4, and at x is equal to 0. Alright, well, the first thing, at x is equal to -1, the function what? Increases and decreases. So x is equal to -1 is an asymptote. Alright, and that simply means that at x is equal to what? -1, the function increases or decreases without bound. Therefore, at x is equal to -1, we have infinite discontinuity. Alright, so that's the first thing, A. Alright, let's see what happens at x is equal to 2. At x is equal to 2 is a similar scenario of infinite discontinuity. So x is equal to 2 is again an asymptote. X is equal to 2 is an asymptote. So at x is equal to 2, we have infinite discontinuity. C, for C now, it's at what? X is equal to 4. Alright, at x is equal to 4, there is a hole in the graph, indicating that the limit exists, but the function is not defined at x is equal to 4. So at x is equal to 4, um, f of 4 f of 4 is undefined, or the limit, or you could say the limit of f of x as x approaches 4 is not equal to f of 4. Alright, in particular because the limit exists and the function doesn't exist, or the function is undefined at x is equal to 4. The function never reaches that value. So we say at that point we're having what? At x is equal to 4, there is point discontinuity. Alright, now at x is equal to 0, you can see that the left hand limit is 1 and the right hand limit is minus 1. So the left hand limit is not equal to the right hand limit. So in such a situation, you have jump discontinuity. So the left hand limit of f of x, the left hand limit of f of x as x approaches 0 from the left is not equal to the limit of f of x as x approaches 0 from the right. Therefore, we have what? We have jump discontinuity. So we have jump discontinuity. Let's talk about removable and non-removable discontinuity. Here, functions with point discontinuity are said to be removable discontinuity. Jump and infinite discontinuity cannot be removed and are classified as non-removable discontinuity. Essentially, the point discontinuity can be removed because you get the point discontinuity when you substitute a value of x into the function and get 0 at the top and 0 at the bottom. Most times that can be avoided by simply cancelling the binomial which is common to both the numerator and the denominator. Alright, let's have a look at example 24. It says, given the function f of x, where f of x is equal to 4x minus x squared for x greater than 2, and f of x is equal to 3x minus 2 for x less than 2, for x less than 2, identify the values of x at which f of x is discontinuous and describe the type of discontinuity. Alright, with a little bit more experience, you'll see that it's obvious that at this point, you're actually experiencing or better yet, we can see clearly that f of x is not defined at x is equal to 2. So the first thing is that f of 2 is undefined. Now, the only thing remains is to see if the left hand limit and the right hand limit are equal. If the left hand limit and the right hand limit are equal and f of 2 is not defined, then we will be having point discontinuity. Let us see if that is the situation here. Alright, so the limit of f of x as you approach 2 from the left hand side would be equal to 3 times 2 minus 2. 3 2's are 6 minus 2, we get 4. Now the limit of f of x as we approach 2, as x approaches 2 from the right hand side would be equal to 4 times 2 minus 2 square. Now 4 times 2 is 8 and 2 square is 4. 8 minus 4 is 4. So the left hand limit and the right hand limit are equal at x as x approaches 2, but f of 2 is undefined. Therefore, at x is equal to 2, we have point discontinuity. Alright, so let's just double check to ensure that we answer the question. So we're asked to identify the values of x at which f of x is discontinuous. So well, f of x is discontinuous, and to describe the type of discontinuity. So I think we did. F of x is discontinuous at x is equal to 2, and the type of discontinuity is point discontinuity. Example 25, and if I'm not mistaken, I think this is the last example. Calculate the value of x that makes f of x discontinuous. Alright, so no, the value of a, sorry, that makes f of x discontinuous everywhere. Alright, I'm guessing, well, first of all, this is in where x, the function is defined for x less than or equal to 3, and it's defined for x greater than or equal to 3. So we're assuming that that the function is defined at x is equal to 3. But therefore, for the function to be continuous, the left hand limit and the right hand limit must be equal. For the function to be continuous, the left hand limit and the right hand limit must be equal at x is equal to 3. Alright, but this doesn't say it's for it to be continuous everywhere. Well, for it to be continuous everywhere, the left hand limit and the right hand limit must be equal. So the left hand limit are for Alright, so for this function to be continuous everywhere, the left hand limit and the right hand limit at x is equal to 3 must be equal. Alright, so the left hand limit, by direct substitution, it would be the log of 2a plus 4 times 3 must be equal to the log of x is 3 of 3 plus 4a. Alright, so therefore 2a plus 12 must be equal to 3 plus 4a. We get all the a's together, so we have what? 12 minus 3 is equal to 4a minus 2a. So 2a would have to be equal to 9. Divide both sides by 2, and we get a is equal to 9 over 2. So for this function to be continuous at x is equal to 3, a would have to be equal to 9 over 2. Alright, so I was wrong. 25 was not the last example. Let's look at 26. At 26, we are told, given the function f of x, determine the value of x for which the function is discontinuous and identify the type of discontinuity. Well, for starters, the function is not defined at x is equal to 1. So x is equal to 1 is the value of x for which f of x is discontinuous. Now, how do I know that? You might ask. Well, the function is defined for x greater than 1. It's defined for x is less than 1, but it's not defined for x is equal to 1. So the function is undefined for x is equal to 1. So it's discontinuous at x is equal to 1. Let's identify the type of discontinuity. Alright, for us to do that, let us find the left hand limit and the right hand limit. So the left hand limit as x approaches 1 from the left of f of x is equal to 8 times 1 minus 4, which is equal to 4. The right hand limit as x approaches 1 from the right of f of x is equal to 4 times 1 plus 2, which is equal to 6. So the function is not defined at x is equal to 1, and the left hand limit is not equal to the right hand limit. So at f of x, at x is equal to 1, 1, we have there is jump discontinuity. Alright, 27. This should be the last question. Alright, given f of x is equal to x plus 1 over x plus 2, determine the values of x for which f of x is discontinuous. Is this discontinuity removable? Alright, for starters, just by looking at it, I don't see this discontinuity being removable. Alright, the discontinuity, f of x is discontinuous at if the denominator is equal to 0. If the denominator is equal to 0, alright, so let's have a go at it. It's x plus 1 over x plus 2. So we have f of x is equal to x plus 1 over x plus 2. So when x is equal to what? 2, f of 2 would be equal to f of 2 would be equal to, sorry, f of minus 2, it should be minus 2. So it's f of minus 2 would be equal to minus 2 plus 1 over minus 2 plus minus 2 plus 2. So f of minus 2 would be equal to minus 1 over 0. Now, minus 1 over 0 is indicating that x is equal to minus 2 is an asymptote. And therefore, the function at x is equal to -2, the function increases or decreases infinitely. So therefore, at x is equal to -2, there is infinite discontinuity. And infinite discontinuity is non-removable. Infinite discontinuity is non-removable. All right, so that brings us to the end of this lesson.